Okay, we're going to continue on here. We're going to actually go up a chapter there. We'll come back to chapter 20, which is organic, but we're going to do nuclear chemistry first here, which is the chapter 21. And so in this chapter, we're going to obviously talk about nuclear chemistry and how to balance nuclear reactions and equations. And we'll talk about some radioactive decay. We'll touch upon some kinetics like we did before. And then obviously we'll continue on here. So let's talk a little bit about radioactivity. Good talk. Let's go back. All right. So radioactivity or radioactive nuclei will spontaneously decompose into smaller nuclei through radioactive decay. And radioactive decay basically occurs when things are sort of unstable. So a lot of times what will happen is as they're going through sort of radioactive decay, they will emit certain types of particles in that process. And a lot of times energy is also associated with it. We're going to talk about some of the different sort of particles that get emitted in these processes. When we have something that's sort of undergoing radioactive decay, sort of the original guy is sometimes referred to as the parent nuclide. And nuclei is sort of the nucleus undergoing radioactive decay, basically. And the sort of nuclei that's made is sometimes referred to as the daughter nuclei. So it's sort of the thing that sort of results from that substance that's going under radioactive decay. Pretty much on the periodic table, anybody kind of like 84ish or more protons are going to be radioactive. So that usually will put us kind of on the bottom row there on the periodic table where we have our actinides series where uranium and all that is there. A lot of those guys are radioactive. Also, a lot of the man-made ones are as well. Elements are also radioactive because, well, that's sort of how they make them in a sense, is they kind of shoot some particles at isotopes and they become other sort of things. Now, there are some definite different types of radioactive decay that we're going to talk about and some different types of particles along the way. So our friend Rutherford, you remember him, hopefully, right? He did something with some gold foil and shot some alpha particles at it. Basically describes some different types of radioactive sort of rays that we come across, or particles. The first one is alpha particles, and alpha particles, as we will see, is sort of abbreviated a couple different ways in nuclear chemistry. They will use the alpha symbol, obviously, and they'll have a 4 and a 2 up there. And it is also sometimes and very commonly sort of used as a symbol as helium. And that's because alpha particles are pretty much helium. So they'll also use helium as sort of the symbol as well. We hopefully remember when we see an isotope written like this, right? The number on top is yes, it's the mass number that's up there on top, right? And the one on the bottom left there would mean that would be good. That's the atomic number. I'll try double jeopardy here. Atomic number is the number of protons there are, right? So there's the number of protons that there are in an atom. Mass number is the number of protons plus the number of neutrons that you can find in there. We can find, obviously, as we'll talk about, the atomic number is found on the periodic table, right? It is the number above the symbol. Every element has its own atomic number. So really, if you know the atomic number, or you know the number of protons, which is basically the same thing, you know what element you're talking about. It also will tell you the number of electrons if the substance is neutral. But a reminder that the actual definition of atomic number is actually just the number of protons, not electrons, so just number of protons. The mass number cannot be found on the periodic table, by the way. The number underneath the symbol is not the mass number. That is the atomic mass of the element, which is different. A good way to remember that is that whenever you are asked, for example, to calculate protons, electrons, neutrons, mass number, atomic number, they all should be positive whole numbers, and clearly all the numbers underneath the symbols are definitely not whole numbers, so they're definitely not the mass number there. Beta particles are also very commonly seen in nuclear chemistry. Also has a couple of symbols as well. They could use the beta symbol with a 0 and a -1 going on there. or because it's also like an electron, you could use the E for like an electron there, for beta symbol there. They basically have a -1 in terms of their sort of charge, because they basically are sort of electron-like. So alpha particles are kind of like positive particles, obviously, and beta particles are negative particles. And that leaves us our gamma rays, which oftentimes is sort of abbreviated like so, with a 0 and a 0. And gamma rays, as you might remember, are really just pure energy. So if you remember the electromagnetic spectrum, where you saw things like radio waves, infrared, visible part of the spectrum, UV, this guy was pretty much at the end of the spectrum there on one side, past X-rays. So a reminder that things that have a very short wavelength, right, has a very high frequency and a very high energy, and that is what gamma rays have, very short wavelengths, really high in energy. Opposite of that, obviously, is things with longer wavelength, lower frequencies have lower energy. So like radio waves are very longer wavelengths, have a lower frequency and a lower energy. In addition, there's some other sort of symbols that we will also come across here. A positron is like an electron with a better attitude. It's like a positive electron there. So it also actually shares the same sort of symbols, if you will, with our beta particles. So they kind of interlap in terms of their symbols. But definitely there is a difference between sort of the beta particle and the positron. And you usually will have some type of distinction to allow you to know one versus the other. So if you're just given like the beta symbol, it's probably pretty safe to assume that it is a beta particle. If they wanted maybe to do like the positron, they definitely will put a plus maybe there or something like that to indicate that it's the positron. So there usually will be some type of indication that it is, even though they kind of share similar sort of symbols. There's also sometimes what will happen is what's referred to as an electron capture. And that again is just an electron symbol, like normal is what's usually used when we see it. Now, there are some words that we kind of talk about in terms of radioactive decay, and that is if anything goes through radioactive decay where it emits a particle or goes through this type of radioactive decay, usually those particles will end up on the product side. So anything where it's being emitted or anything like that, that's sort of where those particles will end up. The other option is you can have something like an electron capture, which means that guy is going to actually be on the reactant side. Also, the word bombardment, like you bombard something with a particle, also means those particles will end up on the reactant side. So probably in a good majority of the time, your particles will kind of end up on the product side, but there are a couple of cases, obviously, where you bombard something or you have some type of electron capture where those particles will actually end up on the reactant side. So there's our atomic number and our mass number, and clearly, again, we write it like that, which is very common. Another very common thing right here is when we could write isotopes is if you had something like this, for example, 64. So that's copper 64, and this is, again, another very common way that isotopes are written. And the 64 here would be the mass number, right? Because we could go to the periodic table and see that copper is 29, which would be its atomic number. So that's a very common way. Reminder that isotopes are the same element, right? But they have different masses because they have different numbers of neutrons, right? So that is basically what an isotope is. They share very similar characteristics, sort of radioactive thing, isotopes versus non-radioactive, but that's the main difference between them. Here are a few more sort of symbols that we could sort of add to our list. A proton is also sometimes used. And again, there's two sort of symbols for protons, and one is obviously a P with a 1 and a 1, or a hydrogen, which is sometimes referred to as a proton. And that's also because, right, all elements will have protons, electrons, and neutrons, except for hydrogen, which has only a proton and an electron. It does not have a neutron, but everybody else basically has all three of those things. Speaking of neutrons, neutrons also another symbol that we use a lot here, and that's an N for neutron. mass number of 1, atomic number of 0. And again, there's other symbols that we talked about previously as well. Now, when we talk about something sort of decaying through a certain type of process, be it an alpha emission, beta, or whatever it may be, those rays really do sort of travel further than some of the other ones. So, for example, here, our alpha particles not traveling too far into pieces of lead. Our beta particles can travel a lot further, and our gamma particles could definitely travel way, way further through there. And that's why it's important if you ever find yourself perhaps working with radioactive sort of stuff in a laboratory, it's always good to know what type of emitter it is, because again, it could be something as simple as you just need like a lab coat and some gloves and you're good to go. Or it could be something like you need lots of lead and good distance from things, depending on the type of emitter it is. So always a good idea if you ever find yourself working with it, you never know. Make sure you take the time to understand what you are working with and what type of protection that you need. Again, here's a few more of our symbols coming on here. So let's talk about balancing nuclear equations. And balancing nuclear equations is like super hard and a lot different than balancing chemical equations. And I'm really lying. You just need to know how to add, really, just so you know. And so one of the main differences that we have in terms of balancing nuclear equations than, say, balancing a regular chemical reaction is the idea of what happens in a nuclear reaction versus a chemical reaction. In a chemical reaction, we balance everything with coefficients because we have conservation of the elements. And that is because in a normal chemical reaction, pretty much the only thing that's happening is we're going to break apart all the bonds on the reactants, and then they're going to reassemble on the other side as products. And the only thing that we're dealing with in that case in terms of bonds are electrons. So in a chemical reaction, it's all about the electrons making and breaking bonds. Very different in a nuclear reaction is it's all about what's inside the nucleus. So it's all about the protons and the neutrons, which, by the way, that is where you find those guys, right? In the nucleus is our protons and our neutrons. So it's about protons and neutrons changing. And as I talked about a second ago, obviously the number of protons is important because every element has its own number of protons. So in nuclear reactions, as we change the number of protons that we have, we are changing the elements. So there's really no conservation of elements in a nuclear reaction because basically all of our protons and neutrons perhaps are changing a little bit. By the way, a word that sometimes pops up a lot is what is referred to as a nucleon. And a nucleon is basically the protons and the neutrons. It's really the stuff that makes up the nucleus. So those are obviously the particles that are found in the nucleus. So the way that we approach sort of balancing nuclear equations is pretty simple. When you add up all the mass numbers on the left-hand side, so in this case, looks like a 236, and you add up all the mass numbers on this side, which is a 138, a 96, and you do need to multiply the coefficient there by the number on top. So that would be 2 times 1, which would be 2, gives us 236 on the right-hand side, and that would be technically balanced. And the opposite is true here, or the other thing that you need to do is all the atomic numbers on the left-hand side. So in this case, adds up, looks like to 92. Will add up to all the atomic numbers here on the right-hand side. So pretty much simple adding, maybe a calculator and a periodic table is really the thing that will help you sort of balance nuclear equations. Now, clearly in a problem, it could appear one of several different ways, but maybe something is missing. So for example, if we had our equation here, where we had our 235 and our 92 and our 10, and then we had a 138 and a 55, and then maybe we don't know what that is, but we had our 2 neutrons. So maybe there's something missing and we want to figure out sort of what is the missing thing. Out of those 2 numbers, really the most important thing to figure it out is going to be the atomic number, because we can use the atomic number, we can use the periodic table and pretty much figure out what is missing. So to do that, it's just some simple math. We'll go 92 on the left here. On the right, we have 55 and 0, which means we have 55. So basically, if we take 92 minus 55 in this case, we should get 37. Once again, we would go to the periodic table and find lucky number 37 there, which is RB, which is what we see here. So we would know, okay, this is RB and 37 is sort of the missing guy. We would do pretty much the exact same thing for the top guy for the mass number. Again, on the left here, we had 236. On the right, in terms of on top, we had 138, and we also had 2. And once again, you do need to multiply that coefficient, by the number. We did it on the bottom as well, but it was 0 for the number on the bottom. So 2 times 0 gave us 0. So that's obviously why that was like that. That would give us a 140. And here's where maybe the calculator comes into play. 236 minus the 140. Hopefully, I'm going to say gives us 96 there. And that would give us, obviously, our missing sort of mass number. So I would approach it by obviously finding maybe the missing atomic number, use the periodic table to figure out what element's perhaps missing, and then obviously do the math there to figure out the mass number. Any questions on that there? Now, a reminder, though, that although probably in most cases, the missing thing will be an element or something like that, but it is possible that the missing thing is like a particle. So it could be like a neutron, maybe an alpha particle, which you would still be able to figure out from the periodic table. Could be a beta particle or something like that. But I would say probably in most cases, it'll be some type of element. But if you do it and go, that doesn't really match up maybe to an element because my atomic number is 0 or something like that, then it might be some type of particle that might be missing. So that's what you would want to look at. Any questions on that there? All right. All right. So why don't you try one here? Why don't you write the balanced nuclear equation for the alpha emission of PO 212. And on the periodic table there, PO is number 84, I think. 84 is PO. Okay, let's take a look and see. So once again here, we're going to start with our starting guy here, which is 212. Again, we go to the periodic table there and get the number above, which will give us our atomic number. Now, this is going to decay through alpha emission. So the key word there is emission. That tells us that the alpha particle will be on the product side. It's going to like it's being given off. So for the alpha particle, you can do it whichever way you want. You could use the helium as a symbol. You could use the alpha symbol. Either way that you want to do it is okay. But that's going to help us here. We're going to look on the left there. We got 84 for the atomic number. On the right there, we have 2. So if we subtract that, that means really our missing atomic number there is going to be 82. And we would go to the periodic table. Number 82 is our friend lead. Now we will do the exact same thing for our mass number. So if we look at the mass number there on the left, that is 212. On the right, we do have a 4. So it's like a lot of math there. That's like 208. I'm going to go with without the aid of a calculator and hope for the best. That's going to be 208 there. And now this would again represent our balance equation. And again, you could absolutely use the alpha symbol there if you like. Any questions on that? Yeah. It is. So that's basically it's basically what the alpha particle represents in terms of the mass number and the atomic numbers. So always will be 4 and 2. Yeah. So that chart that we saw earlier with all the different particles and the numbers, those are important numbers to know. So they'll help you balance it. So like a proton's 1 and 1 or a neutron's 1 and 0. So those numbers that go along with those symbols are really important for things like this to help you balance those equations. Yeah. Other questions? So as I mentioned earlier, there is that sort of difference between chemical processes and nuclear processes. And again, the two major differences is one of them we talked about, which is again, chemical reactions. It's really all about our chemical reactions are really all about the electrons gaining, losing, breaking bonds, making new bonds. There's really no change to any protons or neutrons in a normal chemical reaction. But really, as we talked about, that's pretty much what everything's happening there in a nuclear reaction. It's really all about kind of neutrons, protons kind of being converted to one another. The other major difference, as we will see as well, is there's a major difference in terms of energy that can be sort of given off, if you will. In a pretty exothermic reaction, it's going to be kind of nowhere near what's going to happen in a sort of fission reaction or a nuclear reaction. And that is also because in a nuclear reaction, we're playing with the nucleus, right? Which involves a lot of, obviously, energy change to kind of make those things change. So there's a big energy sort of difference that occurs, and usually will release a lot of energy along the way. So let's take a look a little closer at each of these sort of decay processes, or some of these decay processes, and what's sort of happening. So in this, these are our beta decays. And again, we can see our beta symbols here. We're not going to worry about these guys, which are neutrinos. They're not going to really factor too much into what we're going to talk about here. So you don't have to worry about those guys. But what's really happening when we have something that has or gives off a beta particle is we're really decreasing the neutrons by 1, and we're increasing the number of protons by 1. But what's really happening is we're kind of transforming a neutron into a proton. So the result of transforming a neutron into a proton is we're going to kind of give off this beta particle in that process. So that's what's going to be given off in that process. So overall, because the beta particle has a -1 for the atomic number, you actually kind of go forward on the periodic table to the next element is basically what happens. And that's what we see there. We go from carbon, which is 6, to nitrogen, which is 7, and 7 and -1 is 6. So that balances out in that particular case. Same thing here with potassium. We go from 19 to 20. Again, 20 and -1 is 19 on both sides. So everything balances out correctly. In terms of the mass number, it really doesn't change overall from beginning to end. But if you kind of do it step by step, which is not exactly correct, but just to show you sort of what is happening, if we take something like 14 and our 6 carbon, and basically we're going to lose a neutron, which means that the mass number would actually lose 1, right? Because that's protons and neutrons up here. And this guy's just protons, right? So if we did that, technically speaking, at some point along the way, we dropped the 13 and 6, and we're still carbon. But then we now gain a proton, which means we're going to add 1 to each of those numbers, which will take us back up to 14. This will take us to 7, and now we become basically nitrogen because we made that proton. So we're kind of switching out a neutron in the mass number for a proton. The net result of that is the mass number basically stays the same in that particular case. Any questions on that there? Okay. When we look at a positron emission, once again, we can use kind of the same symbols, but it is, again, a positive versus a negative. And as I mentioned before, occasionally they'll do that for a beta particle. They may do that for a positron particle in that particular case. In this case, what's happening is we're actually going to do kind of the opposite. We're going to take a proton and kind of convert it out into a neutron. So really the same thing happens in a sense in terms of the mass number. If we just kind of do our little step-by-step process here, we lose a proton, which means we're going to actually lose a number in both of those spots. And then what happens is we make a neutron, which means we're going to put a number back into that spot right there. And that will get us back to what we end up with. So again, overall, there's kind of no net change in the mass number, but really what's happening is we're dropping a proton and replacing it with a neutron. So that's why, again, the number stays the same, but there is some transitioning sort of occurring. And obviously here, we actually will decrease by 1 on the periodic table because we are giving off that beta particle. Now, an electron capture, as I mentioned earlier, the electron capture means that we will have the electron on the reactant side. So that's what the capture part sort of means. And in this case, we're actually going to take a proton and an electron, put it together, and we're going to make a neutron as a result of that. And again here, the end result is we get no change in the mass number, but once again, we're going to lose a proton, which in the first example would take us to 36. but then we're going to put a neutron back in that takes us back to 37. So again, overall, the number doesn't change, but there is, again, some transitioning of those subatomic particles. And in this particular case, we end up with 17 for chlorine in this example, which matches the -1 and the 18, which gives us 17 on that side. Probably the biggest sort of change that occurs is an alpha particle. And in that case, we really decrease the mass number by 4 and increase the atomic number by 2. Now, fission is a nuclear reaction where it can happen really one of two ways. And one way that it could happen is just spontaneously. And spontaneously, you could have a isotope that decides it's not very happy, and it will go through the process of fission. And basically, the process of fission is you start with sort of a unstable sort of nucleus, and it splits off into two new nucleuses or isotopes, if you will. It also usually will give off some neutrons, and usually will involve a lot of energy sort of being given off as well in that process. As we'll talk about, even though it will split off into two new nucleuses, it's not always going to be the same two every time. So even if you start with the same thing, it may split off differently, but typically you usually will get two new isotopes formed. You definitely will get some neutrons coming out and usually some energy as that process of fission. And it usually occurs in sort of a unstable sort of nucleus that, wants to kind of split off and maybe become a little bit stable or in those processes. Here's a table, and you have a similar table in your book, and obviously it's all what we just were talking about in terms of our particles there. All right, so why don't you try this one? Write the nuclear equation for potassium 40. Potassium is number 19 on the periodic table. Okay, let's take a look at this one. So we'll start again with our potassium. We'll do a 40. Once again, you can go to periodic table and get the atomic number, which is our number up there on top, and that's going to be a 19. This again is a positron emission, so that means our positron particles should be on the product side. And again, you do have a couple of options in terms of how you want to do that. You can use the beta symbol there, or you can use the E if you like as well. That's all good. So again, you could also do this, whichever way you like to do it. That's going to help us get to our missing atomic number. So in this case, in terms of our atomic number, on the left-hand side, we have 19. On the right-hand side, we have 1, which means 18 looks like our missing guy. And we go to periodic table, we can see number 18 is argon. Now for our mass number, not too bad. We got 40 on the left, nothing on the right, which means 40 should be our missing mass number in this particular case. Any questions on that there? All right, so I want to try a few more here just to make sure. Maybe. There you go. All right, so write the balance equations for each of these, see what you come up with. Okay, let's take a look, see how you're doing. So we'll start with the first one. We got uranium. Remember, should go up on top. Once again, we could go to the periodic table, get our atomic number. It looks like a 92. This is going to be an alpha emission, which means our alpha particle there should end up on the product side. Once again, you can use the alpha symbol if you like. That means we could use that to get to our missing atomic number. So that's 92 minus 2, which is 90 in this case. And 90 looks like TH. And for our mass number up on top, we got 238 on the left and 4 on the right. So that's a 234, I believe there. Questions on that one there. Coming to the next one, which is neon. Again, that's going to be neon 24, I think it says. Periodic table tells us neon is number 10. This is also going to be an emission, which means our particle should be on the product side. It's a beta emission, and that's going to 0 minus 1. Again, because this is minus 1, we actually have to go up to 11, right? Because 11 plus minus 1 is 10. So we do need to go to 11 on this side, and that will be sodium on the periodic table. And once again here, 24 minus 0 will get us 24 in this case. Positron emission of nitrogen 13, so 13 and 7 from the periodic table, which is nitrogen's atomic number. Once again, we got our emission, so that's going to be the positive one here. And in this case, we have 7 on the left and 1 on the right, which means our missing atomic number should be number 6, which is carbon in this case. And up on top, that's 13 on the left, 0 on the right. So 13 minus 0 is 13. Any question on those so far there? Lastly here, we got beryllium, which is 7. And then from the periodic table tells us our atomic number is 4. This is actually an electron capture, which means the electron will be on the reactant side. And you should use the E for this guy because it is an electron, not really a beta particle. So make sure that you kind of use the E. In this case, we're just going to add the bottom in this case. So we got 4 and minus 1 is 3 is missing. Once again, 3's atomic number is lithium. And for our top there, 7 and 0 is 7 in this case. Any questions on balancing nuclear equations? Sounds really difficult, but really, perhaps a calculator and a periodic table, you should be okay, I think. Obviously, knowing again those mass number, atomic numbers, really important to do this. Yeah, so you got to know, what a neutron, proton, their numbers go with as well. All right, then let us continue on if there's no question. And the first thing we're going to talk about is a little bit about stability. And stability, one way that we look at stability of nuclei is with sometimes referred to as the N to Z ratio, N being neutrons, N being neutrons. Z is, as you remember, the abbreviation for the atomic number, which is basically our number of protons. Yeah, so it's basically our neutron to proton ratio basically is going on there. And again, Z technically is the atomic number. Now, there is an area where I guess a ratio is the better way maybe to say that, is also sometimes referred to by a couple of different names, but there's this area of a ratio of neutrons to protons, which is considered stable. And this is sometimes referred to as the belt of stability. Some people like to call it the valley of stability, amongst other names. But valley or belt of stability are really the two sort of common names for it. And that's sort of the ideal ratio for a particular isotope. And it is really based on, as we will see on the next slide, it's really based on the number of sort of protons that guy has. So depending on the number of protons, there's sort of an acceptable sort of ratio. Now, when you go to calculate this ratio, you could find yourself being too high, which frankly means you're kind of this side of the valley of stability there. And in order to sort of bring it back down to a more stable ratio, what happens is that unstable nucleus will go through radioactive decay, and it actually will go through a beta decay process. So if you find yourself too high from the valley of stability, to sort of bring yourself back down to that valley of stability, that guy will undergo a beta decay process. Now, the other option is you might find yourself a little bit lower than the belt of stability. And if you are a little bit lower than the belt of stability, your guy will go through really one of two processes. It will go through either a positron emission or an electron capture. So it could go through a positron emission or an electron capture. It could also go through an alpha decay, but it's not as efficient. For us, we will kind of simplify it. We will just say if we are too low, it will go through one of those two processes, either a positron emission or a electron capture. Now, we just did an electron capture on the previous one, which was beryllium 7. So we did beryllium 7 there, and we did an electron capture, which looks like this. And we ended up with a lithium, right? Now, if you did an electron capture or you did a positron emission, it will end up the same place. So we did our beryllium here, and it did a positron emission, which would look something like this, you would end up with the exact same guy. So that's why on that one, you kind of have two options, because you will pretty much end up with the same guy as a result of it. So that's why when we're too low, we can have those two options, positron emission, or electron capture, which will end up with the same product as a result of it. Again, if we're too high, it's going to go through a beta decay. Any questions on that there? Okay, so let's take a look at that belt of stability or valley of stability here. And that is our valley of stability. And if you have a sort of isotope or a nuclei that has a atomic number of 1 through 20, the sort of acceptable valley of stability there is basically a ratio of 1, basically. So the ratio of neutrons to protons is 1. If you're somewhere between 20 to 40, it goes up a little bit higher as it being 1.25. And if you're anywhere in the neighborhood of, again, the atomic number there being 40 through 80, it is 1.5. Anything above 84, as we talked about, pretty much going to be radioactive, so it's not going to be stable. So you don't have to worry about it. Now, there is sort of some gray area, as you can see from the cutoffs here. The first one goes to 1 to 20. The next one goes 20 to 40. And the next one is 40 to 80 there. And to make it a little bit simpler for us, and not everybody will kind of do this, but for us in here, if it is 1 through 20, we'll do a 1. If it's 20 through 40, we'll do a 1.25 and a 1.5 for anything that is 40 through 80. It either is that number or it's too high or too low. So that's how we're going to simplify it. It's either that number or, again, too high or too low. The grayish area is obviously in the 20th range. They'll go, well, it's not exactly 1, but it's not exactly 1.25. So, you know, it's still okay. And there's a lot of that sort of grayish range. So we'll kind of take that out of it and just have these as hard cutoffs. And I'll try to remember not to give you one that's like 20 or 40 or something like that. So you won't be exactly at that transitioning point. But just be aware in books and stuff, obviously, there's that grayish area, kind of those transition points between them. So once again, if we are too high, we'll be up here. We'll do our beta to bring us back down. If we're too low, we'll do, again, either that positron emission or electron capture to bring it back up. All right, so let's take a look at one here. You decide here. We have magnesium 22. Predict what type of radioactive decay will it go through. Magnesium is number 12 on the periodic table. Let's take a look. So we got magnesium 22. Once again here, we can go to periodic table to get our atomic number. Obviously, our atomic number gives us our number of protons, which is 12. Our neutrons, again, are found by subtracting the mass number minus the atomic number. That gives us 10, right? Because mass number is protons and neutrons, and atomic number is protons. So if you subtract them, that is how many neutrons you have in this case. Basically, top number minus bottom number. That gives us our way to calculate our N to Z ratio. So we're going to take 10 divided by 12, going to get us a 0.8333. Now, this is an atomic number of 12, which means technically it falls in that 1 to 20 range, which means the acceptable ratio is 1. So in this case, that looks a little too low. So we're like here, we need to bring it back up. So because it's too low, it could go through one of two things when it's low, right? Either electron capture or positron emission. And if we wrote the equation there for our electron capture, we would end up with an 11, and up on top 22, and that should be sodium, which is number 11. Again, the other type of process it could go through, which will yield the exact same thing, is our positron emission. And once again, on the bottom there, we will end up with 11 and 22, which would be sodium in this case. So it would go through one or the other sort of emission here. And we could actually look at what it would make and see if it did get any better in terms of the ratio. So if we looked at the sodium, sodium would have 11 protons, and in terms of neutrons, the sodium would be 22 minus 11, which is 11. Now, when we do our N to Z ratio, we are 11 over 11, which is 1. So in this particular case, just by going through that one process, your electron capture or the positron emission, we actually got a perfect ratio, a nice stable thing that has occurred. Does not always happen. Yeah, so you won't always, after the first decay process there, hit something that's perfect, but it definitely should move you in the right direction. So if you were too low, it definitely should kind of bring that ratio up a little bit, and vice versa. If you were too high to begin with and you did it, it should kind of bring your ratio down a little bit. Occasionally like this, you may actually bring it down or up to like the perfect ratio, but it may not always occur, obviously, the perfect ratio. And if you do have a problem like this, you do not need to keep doing it until it gets perfect. Usually just the first sort of step there is sufficient. Any questions on that? Yeah. Our the ratio. So if you are too low from this belt of stability here, basically the way it could fix it is one of two things will occur. Either it could do an electron capture or a positron emission. And if you calculate the ratio and you're too high, like you're up here and you need to bring it back down, really the only thing that will happen in that case is a beta decay. So it's really based on sort of the acceptable ratio for that particular guy and kind of where you fall. If it's too low, you have the option of those two things to bring it back up. Or if it's too high, you have the beta decay, which will bring it back down. Yeah. Yeah, technically you can write either one. It's fine. You don't have to write them both. You know, if you either one is acceptable because they both really end up in the same spot in terms of what the outcome is. So you don't have to, but you can if you want. Yeah. Yeah. You could do an alpha decay. Is not as efficient. So for us, we're not going to use that for this. Again, you should be aware of. You can still technically use it, but these are the much more sort of efficient route to kind of get there. Yeah. Yeah. Electron capture or positron emission. Beta decay. Other questions? All right, let's try another one and see here. So let's do Krypton 85. And Krypton is number 36 there on the periodic table. Okay, so we got Krypton 85 and 36 from the periodic table as our atomic number. Again, that obviously gives us our number of protons, which is 36. Number of neutrons, we want to take our mass number minus our atomic number. So that's going to be us 85 minus 36, and that's going to give us a 49, it looks like. So our N to Z ratio here is 49 divided by 36, going to give us a 1.36. Now for our acceptable sort of ratio here, we are looking at a guy that is between. He is 36, so that is our 20 to 40 cutoff, which would be 1.25, I think, is the acceptable one. So as it is 36, right? So we are definitely a little bit high here. So we want to drop it back down. So in this case, it will go through a beta decay. So we'll have our 85 or 36 krypton. Going through our beta decay will get us a missing atomic number of 35, looks like. And once again, 35 from the periodic table there is bromine. And our mass number would be 85 in this case. Now we could kind of check and see if we're at least moving in the right direction. So we would have 85 minus 35, which is 50 neutrons. And divided by 35 gets us 1.46. I feel like I did not go in the right direction there because I went the wrong way. You see that? I know you were just about to tell me that I did the wrong one there. We'll fix that in post-editing later. All right, so let's try that again. Take two. Here we go. Beta particle. So since that's -1, perhaps I need to go up to 37. Will give me, that's right, you should use the calculator maybe. 37 and -1 is 36. That seems better. Let's go with RB. and that would get us 85. Oh, I bet you we will be going in the right direction, hopefully. That's going to give us 48 in terms of our neutrons, and our protons in this case would be 37. So let's see how we did in this case. That's a little bit better-ish, I guess, 1.3. That's definitely going in the right direction. We're coming back down. As you can see, in this case, we did not come down perfectly, but we are moving in the right direction, provided you do the math right. Yes. Any questions on that one there? Yeah. Yes. Yeah, so you don't have to keep doing it until you get to 1.25. So you, in these type of problems, you can just do the what's in the box there. But you should check it like I did in case you screw up like I just did there, right? You could see that when you did the one I messed up on, we were actually continuing upward, which is not what should be happening. Obviously, we should be continuing downward. So it's a good way to check yourself. Again, you may not hit perfect ratio, but you should be moving in that direction from where you started from. Other questions on that? Yeah. Yeah, the daughter nuclei would be this. So this is was sometimes referred to as the parent, and this would be the daughter. So whatever is sort of formed as a result of the decay process, this is the daughter. Yeah. Other questions? Yeah. So N to Z ratio is an important sort of thing. Yeah, that's what it looks like. There it is. Is an important sort of thing in terms of stability. But there are actually other things that we sometimes look at in terms of stability. So perhaps if you don't calculate the N to Z ratio, there is sort of a lot of stable nuclei will have even numbers of protons and neutrons. And that's what this table down here shows you. Kind of the best situation for stability is if you have kind of an even number of both protons and neutrons. There's like 157 sort of stable nuclei that basically have that arrangement. The next sort of best thing is even protons and odd neutrons. They're dropped significantly, though, down to like 50 some odd that have that arrangement. Next best thing would be odd protons, even neutrons. And as you can see, sort of the worst combination for stability is when you hit kind of odd and odd for both of those things. There's very few sort of stable ones that have that. So sometimes people will just kind of quickly look and go, okay, I got like even and even, that should be relatively stable. Or I got odd and odd, that's probably not going to be so stable. So those are sometimes things that people look at in addition to the N to Z ratio. There's also total number of nucleons. And again, nucleons are protons and neutrons, basically our guys in the nucleus. And if they add up to a magic number, it's more stable. It's kind of like bonding where things try to get to the noble gas configuration. It's pretty stable. Is that sort of idea. Also, we also have a lot of things that are stable when either the neutrons or the protons is 2, 8, 20, 28, 50, 82. And your mega number is 126, in case you want to play that later. That is the number of neutrons is those sort of stability. I would say a majority of time people will kind of look at the N to Z ratio, that even and even. And later on in this chapter, as we'll talk about, they'll also look at what's referred to as binding energy per nucleon is another way that you could look at stability. So those are sort of common ways. Now, when things aren't stable, they will sometimes go through what is sometimes referred to as a decay series. And that is basically when the substance will continue sort of down this decay path and go through radioactive decay until it kind of hits something that's relatively more stable. So it'll kind of continue through multiple decay processes, one after another, until it pretty much hits that stable nucleus. Now, if you don't want to kind of write out the entire sort of step and process and write the equations, and you're dealing with just beta decays and alpha decays, you could kind of just do it math-wise and go for every alpha decay, you subtract 4 from the mass number, and you subtract 2 from the atomic number. And for every beta decay, you basically add 1 back to the mass number. So for example, if we were to look at sort of a decay process here, I'll show you both ways that you could kind of do it. Let's say we started with uranium-238, and that's a 92. Now let's just say it went through, we'll just do a few of the steps here, alpha, beta, beta, and alpha. Now, if it went through this decay process and we maybe want to know what we get after each of the steps, what we would do is, frankly, just the balancing equation thing that we did before. So we would start with our 238 and our 92 uranium. The first thing that would happen here is it would go through an alpha decay. So we would do our alpha. That would leave us a 90, which if we go to the periodic table, number 90 there is TH. And it will leave us a 234 up on top. Now, what will happen is the product here, or the daughter here, will then go through the next decay process, which is a beta particle. So this guy here will then go through a beta decay, which will then take us, we need to add one. I'm going to do it right this time, 91 there. And again, 91 in this case is going to take us to PA. And we'll have 234 up on top. Then this guy here will go through the next decay process. And it will also be, in this case, a beta decay. Once again, we're going to go up a number. So that's going to be 92 and 234. And 92 there is going to take us back to uranium. Lastly, in my very short decay run here, we're going to do an alpha decay, which are 234, 92 would go through our alpha decay here. And that's going to get us to 90 and 230. And that will be 90 is back to TH. So if you wanted to, step by step, you can basically just write out nuclear equations where the product of the first reaction then becomes your reactant in the second one, and you kind of continue that process, however many decay processes you have. Now, if you were just interested perhaps in what you would get after that short run, you could do it mathematically, and you could start with just the number 238 and 92. And you went through 2 alpha decays, which means from the mass number, I subtract 4 twice. And from the atomic number, I should subtract 2. And you went through 2 beta particles, which means I should add 1 back to the atomic number, which is the bottom. And if I did that correctly, that's 238 minus 4 is 230. And for the bottom there, it's 92 minus 2 is 90, minus 2 more is 88, plus 1 is 89, plus 1 more is 90. And you could get right to sort of the end product at that point if it's beta or alpha decay. So if you're not interested maybe in each of the steps, just what you get at the end, you could kind of do it mathematically, and that's how you could get there. Or if you want to do it step by step, you can, which maybe you might not make as many mistakes. If you maybe do the math wrong, at least you hopefully will catch it. Any questions on decay series here? Now, just to show you the uranium one that we're looking at, as you can see here, it goes through a lot of decay processes, basically until it hits down here to lead to become neutral. It actually can, after the first run here, kind of veer off in one of these 2 processes, but they both will pretty much end up at the same end result, which is our stable lead guy at the end. Question on that there? Yeah. The elements do become different elements because the protons change and stuff like that along the way. Yeah. So that's the major difference between nuclear reactions and chemical reactions. In chemical reactions, we don't do anything with the nucleus. There's nothing involving the protons or neutrons, but really nuclear reactions are all about changing protons and neutrons and stuff like that. As a result, as you change those protons and neutrons, they emit these other particles like alpha particles and beta particles are given off along with energy in that process as well. So that's why we really don't have the conservation of elements when we do these type of things. Other questions? Okay. I think that's a good place to stop.